So, in the last class we looked at the types of symmetry operations and the symbols that we give for the type of symmetry operations. For example, in this very first illustration here you see the presence of an inversion center. The presence of the inversion center is indicated as 1 bar, which actually tells us that if a point x, y, z is taken in 3-dimensional space, it goes to the x bar, y bar, z bar, that means minus x, minus y, minus z. And now we operate the same 1 bar operation on this x bar, y bar, z bar, it will come back to x, y, z. Now, as we defined in the last class, such an operation is referred to as the point group. So, this now represents a point group symmetry, and that is represented by a small open circle which represents 1 bar. So, in literature you may find just this written, or in literature you may find only 1 bar written. And when you want to display the objects and their nature in which they are present in this using the 1 bar symmetry, it is normally represented this way. So, the object is written as a bigger open circle, and this sign positive tells that it is coming towards us, towards me in this example. And then when we operate the 1 bar symmetry, this x and suppose this is represented in the x y plane, then this goes to minus x minus y, and then of course z goes to minus z. That is illustrated by the presence of a comma in the middle of the open circle. So, the operation x bar z y bar is indicated by a negative sign here, which is taking the indicating that this object which is in front has gone to the back side of the plane of this representation. So, essentially we therefore generate 2 equivalent points with a symmetry operation which is the center of inversion, and if the center of inversion in the crystal context is also referred to as the center of symmetry, because the object here and the object there are related to each other by a center of symmetry. That is how we interpret. It also tells us that if by chance the object sits on the center of symmetry, if it is located at the 1 bar position, then you see that it will be represented by, let us say in this particular example, x is 0, y is 0, z is 0, that defines the origin, and the center of symmetry sits on the origin. Then you see that 0, 0, 0 and minus 0, minus 0, minus 0 will represent the same point, and therefore, the number of objects that will get repeated in this point group operation will remain the same. In other words, there will be only one symmetry operation, and that is referred to therefore as a special position. So, in this special position you will have the object both positive and negative indicated at that particular position. In fact, if there is a nomenclature which has to be indicated here, you can remove the open circle and put the closed circle and put a representation which is something like this, which is shown here just to show you the example. This unit, which is half plus and half minus with a negative, can be taken up and put over there, saying that half the object will occupy this position. So, the number of equivalent points in general is 2, and the number of special positions in this particular example is 1. So, the special positions are a special situations with respect to the position x, y, z, and if x, y, z sits at a center of symmetry, which is shown in this diagram at this position, and it could be anywhere in 3-dimensional space. Whenever there is a center of symmetry that is present in the 3-dimensional space, it will occupy the so called special position, and therefore, we will have half the molecule, which if you consider this as a molecule, half the molecule will be present at that position. So, this therefore now tells us the importance of symmetry representation. It tells us the representation of equivalent points. It also tells us how the objects are oriented with respect to each other in this representation. Notice that this representation also is effectively bringing a 3-dimensionality, because we are talking about this object being in the front and that object being in the back, thereby indicating the third axis which is perpendicular to the plane of the representation here. We now go to the next example, which is the so called twofold symmetry, and in this particular twofold symmetry, this is the symbolic representation. It is marked with a close figure instead of an open figure like that. It is a closed unit here. And again you see that the symmetry operations now are for any given operation x, y, z. It is minus x, y minus z, or x bar, y, z bar, which indicates that the object which is shown here undergoes a 180 degree rotation. So, x changes to minus x, y z changes to minus z. This is about the operation is about the y axis. This also tells us that the y axis is now coming perpendicular to the plane of the representation which we have here, and therefore the y axis is now perpendicular and it is coming towards me or going inside the inside this particular representation. So, if that is the case, there is no change in y coordinate, and so the object which is in front remains in front, object which can go to the back remains in the back. So, if you have an object which is now as an open circle with a negative sign, it will now be an open circle with a negative sign. So, both possibilities occur in case of a twofold symmetry. That means to say that the twofold symmetry, suppose let us say for the sake of argument that there is the object which is present on twofold itself. I want you to think about it and see how you write the equivalent points. In other words, if x, y, z is 0, 0, 0, what would be the representation of x bar, y, z bar? Will that be a special position or not? I think it is better you think about it as an audience and as the participants of this particular workshop, rather than I explain it. It is also another issue which comes up here, that since there is no origin definition here, because if we have a object in front, this object is also in front. If there is an object in the behind, the object will also go into the behind part, and therefore the location of the twofold axis could be anywhere along the y axis. This is a very important point. It is not necessary that the twofold axis should coincide with 0, 0, 0. It can be anywhere along the y axis. Hence, this kind of a representation is still valid, that is both plus and both minus depending upon where the twofold is located, which means to say that whenever we have a twofold axis about a direction, that particular twofold axis can be anywhere along that direction and there is no fixed origin for that. This we will see more in detail when we look at the monoclinic symmetry and the way in which the space groups develop. We have not introduced the word space group as yet, but once we introduce that, we will see how it operates. I also want you to look at this particular representation and see that it is represented as 2 bar. I also want you to look at this and make sure that 2 bar is equal to m, where m is the mirror symmetry. So, the equivalent points there will be x, y, z and x, y bar z, and that is something I leave again for you to work out as a home exercise. So, if you look at this particular representation, in this representation the mirror plane is indicated in this fashion, saying that the mirror is now coincident with the plane of the representation here. So, that is coincident with the plane of the board, and the operation will take this part of the object to the other part of the object on the other side of the 0, and it will be therefore plus and minus, and you have a 2 bar axis which is nothing but a mirror. So, we therefore have covered now 1, 2 and 3 symmetry operations, and these 3 symmetry operations are all point group operations, because by definition they define the requirement of a group, and therefore these 3 point group operations are now considered among the 32 point groups which we will display later on. The next operation is the screw axis, and in this screw axis operation what we will do is to see the operation is done in such a way that now we have to consider an axis which is coming perpendicular to the plane of the board, and that particular axis has a certain dimensionality. Now, if that axis has no dimensionality, remember when we described the twofold symmetry, we said twofold can be located anywhere along the y axis. Now, it is important to define the 0 of that twofold axis, because there is a translation component associated in that direction. That means this operation will exist only in crystalline materials. So, the so called translation involved symmetry operations like the 2-1 screw symmetry will exist only in crystalline operations, crystalline objects and crystalline materials. Here again the object which is shown here will now undergo a 180 degree rotation, and then there is a half unit translation along the direction of the axis of rotation. Let me repeat, the axis of rotation is associated with the y direction. The x and z values will now go from plus x plus z to minus x minus z. Now you might see the difference between this representation and the representation over here, where the value of y has also changed, and therefore we have put a comma inside the circle. Here we do not put a comma inside the structure because this has only undergone a rotation of 180 degrees. So this plus remains the same, therefore 0 plus, and to that we add a unit of half, which is a consequence of the presence of the axis in a crystal. So this particular symmetry operation will occur only in crystal systems. That means to say that this 2 1 is not a part and parcel of the point group symmetry. This is a very special symmetry which exists only in crystalline materials. So please note that point. So we will not now cover all the 2 1, 3 1, 3 2, 4 1, 4 2, etc., because these are all operations which will come as a consequence of the rotation axis having a translation component along a direction in a crystal, and we do not want to consider crystalline materials at this moment. We want to consider only operations about a point, and when we talk about operations about a point, translation symmetry is not the component which we have to invoke, and therefore we will consider only this part of the diagram. So we now go to the threefold symmetry. In a threefold symmetry, suppose this is our main object. This undergoes a rotation of 120 degrees, goes to that particular point, and then another 120 degrees will bring it to this point. So this is a threefold symmetry operation indicated pictorially. I have not purposely written the equivalent points because that will come as a part of your assignments later on. So these equivalent points, there will be now 3 of them, and these 3 will be generated. So this assignment will be for you people as well who are in the audience here. So this now operates the threefold symmetry, and this threefold symmetry now gives 120 degrees. So there are 3 objects now generated. Now we take any object in this among the 3, then you operate the threefold symmetry, it will come back to the same object. So the point group definition is intact even in this particular case. As we go further down, we have the fourfold symmetry and the sixfold symmetry, which will follow likewise. In the case of the fourfold symmetry, we will get 4 objects, and in the case of the sixfold symmetry, we will get 6 objects, and these therefore 1 bar, 2, 3, 4 and 6 now define the point group symmetry. The 2 bar operation, which is also the mirror symmetry operation, is also indicative of the point group symmetry. It also tells us the fact that if we have a point group operation, the operation which is now taking that onto itself across the center of symmetry or the inversion center will still be a part of the point group, because this has no translational component. Please note that if we now consider a twofold axis and then operate as inversion center about the twofold axis, these two will now contribute to a point group symmetry. That is because there is no translation component involved in any direction. This is just the change of the axis coordinate, that is x to x bar, in this particular case y to y bar. So there is no change in, no additional component coming like it came in this example where we had x y z and x bar half plus y and z bar. So whenever this additional half comes, it is not a point group symmetry. So you should note that. But however, this operation is valid in crystalline materials, and that will become an additional point group symmetry which can operate, even though it is not classified under the point group symmetry. So if you consider now 3 bar, this now takes the positive to the negative, positive to the negative, positive to the negative. We generate 6 equivalent points. These 6 equivalent points will become 6 equivalent points in case of 6 bar, which is demonstrated in this way. Once again, this could form a part of your assignment. I want you to see why 3 bar, which generates now 6 of these, and 6 bar, which also generates 6 of these equivalent points, are different from each other. The symbols inside are already indicating why they are different from each other. Here is a threefold with a center of inversion at the middle, and here is a 6-fold rotation with a 3-fold symmetry in the middle, and this makes the difference. And similarly we have of course the 4-bar symmetry, which can appear along with the 4 symmetry. There is no additional concept associated with it or additional feature associated with it. It is of interest to note the difference between 3-bar and 6-bar, and to see how 3-bar and 6-bar are different from each other. So these therefore are some of the point groups and the representations in terms of equivalent points, in terms of position of the objects inside this operational unit, and at the same time indicating how many of them, how many objects are generated inside this one unit operation. So these are therefore representatives of the point group symmetry, whereas these on this side are representatives of the symmetry whenever we have a crystalline system. And now we will go to the next slide, where I have indicated the equivalent point operations in case the operations are about in a crystal and they are about various directions. But this particular slide we will refer to later on. At this moment we will just notice that the twofold axis will generate x, y, z. If it is along the a direction, x, y bar z, and if it is along the b direction, it will generate x bar, y, z bar. This will be x, y bar, z bar, sorry, this is z bar. And if it is x, y, z, the c and the twofold axis is parallel to c, we get x, y, z and x bar, y bar, z. I am not introducing the concept of A, B, C at this moment, because we are yet to define the concept of a unit cell, and that is something which we will take up next, and then we will be referring back to this particular slide again, and then we will see how these operations develop. So this brings us to the issue of defining lattices and crystal system. What are lattices and what are crystal systems? As we just now saw from the symmetry operations and the point group symmetry operations, that the operations involving 1, 2, 3, 4 and 6, which represent the proper axis operations, are point groups. So there are 5 point group symmetries which come up from this context, and another 5 point group symmetries which come from 1 bar, 2 bar, 3 bar, 4 bar and 6 bar. So totally we have therefore 10 point group operations which can come from here, and 3 additional ones, proper and improper axis, which come from this. This we have already seen in the previous class. So you see that in the case where we have a no symmetry or a 1 bar symmetry, which is also the proper and improper axis generating the same 1 bar symmetry, it is now required that we have to define a crystal system associated with this symmetry operation. It is also required to define a lattice symmetry associated with this operation. Now what is a lattice and what is a crystal system? A crystal system is one which represents essentially the dimensions of the unit cell. Now we saw in the very first couple of classes that we saw the Escher's diagrams, and there we defined a unit cell. Unit cell is the one which now repeats itself in all 3 directions, A, B and C, to generate the entire crystal, but the whatever is present inside one unit cell is exactly the same as in the second unit cell as far as crystalline materials are concerned. There are cases which differ from each other, but essentially we are restricting ourselves in this course to crystalline material which display unit cell symmetry, and this therefore is referred to as the unit cell. The dimensions of the unit cell define the so called crystal system. The dimensions of the unit cell are defined with respect to the 3 axes A, B and C, the 3 axes A, B and C, and the interaxial angles alpha, beta, gamma. So these 6 parameters define the nature of the unit cell, and therefore this now refers to the way in which A, B, C, alpha, beta, gamma come up refers to the unit cell, and therefore it refers to the crystal system. The lattice repeats these unit cells in all 3 directions. So essentially when we talk about a lattice, it is like a framework. The framework is built up of ABC, alpha, beta, gamma, which is the unit cell, and now we can move the unit cell along the lattice points. So the edges of the unit cell, if we are considering them as lattice points, the edges of the unit cells now will define the lattice points which now can be put across translations along A, translations along B, and translation along C directions. And therefore, we will generate these unit cells in such a way that we have the A, B, C directions repeating the translational periodicity. The fact that we have translational periodicity in crystalline lattices and crystal systems produces the lattices. So, the lattice sometimes is described in textbooks as an imaginary concept, because the lattice can be present anywhere, whereas the unit cell, once we define the origin, will be associated with the origin of that unit cell, and therefore, the value of A, B, and C, alpha, beta, gamma define the unit cell. So, the crystal system, therefore, which now is defined in terms of the unit cell and with respect to an origin, is unique with respect to the arrangement of molecules or atoms inside that particular moiety. Once whatever is there in the unit cell gets repeated in the following unit cells, that is controlled by lattice translations. These lattice translations are again A, B, and C in 3 mutually perpendicular directions, but however, this lattice can be infinite. So, the points which we consider now need not be the ones which are associated with the origin which we have defined. It can be anywhere in the 3-dimensional space, but the repeat unit will still be the same, and that is why the term lattice. It is something like, we have a window and we have made a frame for the window. The same frame can fit all the windows which have been put in that room because of symmetry, and so we can take the framework from one point to put the framework on the other point. So, the movement of the framework is independent of how and why these lattices are made. This can be considered a lattice. So, that is why in some textbooks lattices are defined as imaginary concepts. There is nothing imaginary about it. It is just the framework which can be slided along the already well defined unit cell concept, which has the translational periodicity. So, the presence of the translational periodicity makes it a realistic definition. So, we very often refer to in crystallography to unit cells and determine the unit cell, and once we have the unit cell determined and the crystal system identified, we will say that we have already got the information about the lattice. The nature of the lattice is evident in terms of determining the position of the location and directions of A, B, C, alpha, beta, gamma, and therefore, the definition of the unit cell. I think that will become clear as we go along when we define it in terms of pictures, but what I see here is what I show here in color is the crystal systems which develop by single proper axis or improper axis or proper improper axis being present in the system. Suppose there is a crystal system into which an object goes into, and that particular crystal system has only one axis of rotation. Of course, one is 360 degrees. The 1 bar operation is the presence of the inversion center, and therefore, there is, if we now want to define a unit cell being of course in 2 dimensions, I will represent the unit cell like this. We will see the plane lattices in a minute. Suppose I say that I have a unit cell, this is the origin. Suppose I say this is A, that is B. Then you see the value of A, the value of B, and value of C depend upon where is the axis located and in what way the objects move around that particular axis. So, since there is no axis with respect to one, it is a 360 degree rotation, and the only possibility is the presence of a center of symmetry, let us say it is located at this particular point O. We do not have any restrictions on the value of A and B, and we also do not have any restrictions on the value of gamma, the angle between A and B in this particular plane. So, by convention, the angle between A and B is gamma, the angle between A and C is beta, and the angle between B and C is alpha. So, that is the convention. So, the ABC alpha beta gamma have no significance when we have only a single operation which is now a 360 rotation. So, if the axis of rotation is one-fold, then there is no restriction on the values of ABC alpha beta gamma, and that defines what is known as a triclinic system. When we go further and go to the presence of a twofold axis, the twofold axis now has the restriction of XYZ should be going to X, XYZ should be going to minus x, y, minus z, assuming y is the direction of the twofold axis about which the twofold is located. So, x y z and x bar y z bar are the two equivalent points. If this restriction is put because of the presence of the twofold and because of the presence of the twofold with an inversion center which makes it a mirror symmetry, or because of the combination of twofold and a mirror which is perpendicular to the twofold, then the values of A, B, C, alpha, beta, gamma will change, and later on we will see this then becomes what is known as a monoclinic system. Now, in a monoclinic system, therefore, we have no restriction on ABC values, but alpha and gamma have to become 90 degrees if we consider y axis as what we call as the unique axis. We will see them in terms of pictures as we go later on to make it very clear. So, what I want to show here in this particular part of the talk is to say that there are independent single axis operations, and along with these single point operations, if we make them also improper axis and consider the combination of proper and improper axis, which effectively makes it the consideration of 13 point groups. Among these 13 point groups, we can have 1, 2, 3, 4, 5 crystal systems. And in fact, the triclinic system, the monoclinic system are more or less unique with respect to these allotments, whereas the trigonal, tetragonal, hexagonal systems, as I have indicated here, the trigonal, tetragonal and hexagonal can also have more than one axis in addition. We have already seen this one axis operation, more than one axis operation, and if it is more than one axis, the Euler's theorem takes over, and based on the Euler theorem we must have a third axis coming in. All these details we have already seen in the earlier classes, and therefore trigonal, tetragonal and hexagonal can have more than one axis. So, the presence of the proper axis and improper axis single axis operation uniquely generates triclinic and monoclinic systems. Trigonal, tetragonal, hexagonal have this. Along with that, we can also have more than one axis that may be present. And orthorhombic and cubic systems, on the other hand, have more than one axis intersecting at a point. And that is why the two systems have some special properties. What special properties get introduced onto these crystal systems, starting from trigonal, triclinic to the cubic system, we will examine when we examine the 7 crystal systems in the next coming 2 classes. However, the take home lesson from this last half an hour discussion, the take home lesson from the last half an hour discussion is essentially the following. We have looked at the operations of the point group symmetries. We have seen how the point group symmetries take the object to different object and again bring it back to the same position, obeying the definitions of a group. We have also seen the operations like the ones which involve a translational part of the periodicity. In case of B symmetry, it is half and so on. And we also have seen how they generate these lattices and crystal systems in these generating 7 crystal systems. So, we will stop at this point.